All right, it's 11, so let's start things. I'm me, Dr. Hartman. My office is over there. Um, Office hours Monday, Wednesday, Friday, 12:30 to 2, Tuesday, Thursday, 11 to 2, and I'm also around the building a lot when I'm not in class. In the event of any sort of emergency or disaster, the class will be handled over Moodle and Zoom. Our course objectives for this is to understand the stuff that we learned in Circuits 1 at a significantly deeper level, and then also learn about three-phase power. Textbook for this class is officially Engineering Circuit Analysis 9th edition by Height, Kimmerly, and Durbin. I might should change that to technically be the 10th edition because I believe it is out, but as you guys who have had me before, no, I don't give a shit about textbooks because I record all my videos and all that kind of stuff anyway. That being said, if you just really want to have a textbook, if you go to Google and type CAD ULABI, this first link here is a textbook called Circuit Analysis and Design by Fawaz Ulabi from the University of Michigan, as well as Michael Maharbis and Symphony First from their respective universities. One of them is in California and one of them is in one of the Carolinas, but I can't remember which. This textbook is free and it does a fairly good job at some of the topics that we're going to talk about. The importance here is that it is absolutely free. You're not stealing anything. The authors literally want you guys to have it, to use it. So download it if you so choose. Let's see, disability disclosure stuff. If you need testing, accommodations, and all that kind of jazz, let me know as soon as possible so that we can get things figured out. Class attendance. I'm going to take attendance every day, which I'll do it in just a moment. The official attendance policy is whatever it says in the bulletin. The unofficial attendance policy is you are all arguably adults. If you don't want to be here, see you later. It's not my problem. If you're not physically here, I'm not going to count you on the roll sheet. It should be very obvious that I have a Zoom set up as well where I'm recording everything. Just as a quick thing about that, I am in no way, shape, or form required to offer the Zoom. I am in no way, shape, or form required to record my Zoom meetings. And I am in no way, shape, or form required to upload those Zoom meetings. I will do so at my own pace because I have stuff going on, okay? If you're like, oh, well, I missed the class meeting about, let's say, series RLC circuits or whatever, you can look at any of my other 5 classes that I've taught, circuits 2 on in previous years, quarters, etc., and find that same thing. I'm following roughly the same structure. The example problems will be different than what I work in our class meeting will be different than what I worked in previous class meetings, because for the most part, I make up example problems as I go. So anyway, academic misconduct, official policy is in the bulletin and all that kind of jazz. Short policy is if you're less of a jerk than I am, then your behavior is great, and don't cheat because that pisses me off. Homeworks. A selection of homework problems will be posted on the course's Moodle page at the end of most lectures and are to be submitted electronically. We'll talk about that in a moment. Homework assignments are due at 5 p.m. 2 class meetings after they are assigned and must be properly formatted as detailed on the course's Moodle page. Any assignment submission that does not adhere to the format detailed on the course's Moodle page, scroll down here, will be rejected from grading. Late homework assignments will incur a 20% penalty for each day they are late. So there is a very specific format that I am looking for. That being said, my graders are probably nicer than I am, so they'll let you get away with things for a little while and they'll just start marking off successively more points as you continue to screw up. So just get it right. It's not that hard. And we're going to talk about it now. So on the introduction page on Moodle, there is this document that says ELEN 223 homework formatting example. I'm literally providing you of an example of exactly what I want. This, for what it's worth, is my solution set to a homework set that I used to give in this class. They're not all 31 pages long, just so that you guys don't get too wildly terrified. but you'll kind of see why they can get long in a moment. Let me zoom in here. And yes, I'm also aware that I misspelled the word answer. So this is what I want for the homework, guys. Okay, so I give you guys an assignment sheet. Okay, the first 7 of these assignment sheets, by the way, are already available on our Moodle page. So everything having to do with op amps that we're going to talk about in this class is already available on Moodle. So I have the full assignment sheet, excuse me, where you put your name and CWID in. That's page 1. Page 2 is even more assignment sheet, as is page 3. Looks like page 4 as well. Then we get to our solution. So I have my solution for problem 1 in standard engineering format, meaning that I wrote out the problem statement and all that kind of stuff and the questions. Then I began my solution. You don't have to go into as much detail as I do here using nodal analysis, blah, blah, blah. I can see that. I'm just trying to make it easy for my graders and all that kind of jazz. So here's my solution. I have boxed in my answer. This +2 and this +1 was how many points to assign to this particular thing. So that means I give a shit about units very, very much. More so in this class than I did in Circuits 1. Units are incredibly important. Use them or you will be deducted points very regularly. Continuing on for my solution to part B. Keep it on trucking. My solution to part C. All the way through E, it looks like. Then I have the computer work. So since I used MathCAD to solve these systems of equations, I am supplying that work as well. And I expect you to do the same. So if the system of equations is small enough that you can do it in your calculator, that's perfectly reasonable. There are definitely going to be problems where you are going to have to solve systems of equations that are larger than any calculator that you're allowed to use in this class is capable of handling. So I am expecting you guys to use MathCAD, which is paid for by your student technology fee. Every single one of you has access to it. And I have also put a link on our Moodle page for you to download it, just in case for whatever reason you don't currently have it. I'm expecting you to use MathCAD as part of this class. That is one of 2 software packages that we are going to use a whole heck of a lot. So anyway, just to recap my homework formatting example at this point, we have the assignment sheet that I have provided to you detailing all of the questions in the homework set. Then we had my handwritten work for problem 1. Now we have my computer assisted work for problem 1. And scrolling down, now we have my handwritten work for problem 2. Then it will be the computer assisted work for problem 2, handwritten work for problem 3, computer assisted work for problem 3, etc. This does not seem to be that difficult to me to comprehend. The assignment sheet, your work on problem 1, your computer work on problem 1, your work on problem 2, your computer work on problem 2, and yet somehow some of you guys in Circuit 2 managed to screw this up for far longer than makes any remote amount of sense to me whatsoever. So I'm being extraordinarily explicit in what I want for you to get the formatting points correct. Follow this guide and you're good to go. It's why I give it to you. I know it sounds like I'm ranting more than usual. I probably am, but it blows my mind that some of you are incapable of following what I believe to be simple instructions. All right. So that's the homework formatting thing. Anybody have any questions about it? I know that have what probably seems like an insulting tone of voice right now. That's just how I talk most of the time, so I'm going to pre-apologize for that. Genuinely, if you have any questions about things, I would be happy to answer them. Anybody? Okay. For organization's sake, I have just made a separate section on Moodle for homeworks, okay? So I have homework set number 1, which is effectively just review material. We're actually going to talk about some of this today. And then an online submission portal for homework set number 1. So my expectation here is that you will give me a file using this naming convention, which is why it's there. I am also flabbergasted as to how many students do not understand what the hell that means. Your first homework assignment is due next Monday, March 13th. This little lock thing here. So I actually have this set up to where on March 20th, this submission portal goes away from the perspective of you guys, meaning that at a certain point, you can no longer submit late homework because it's not worth anything and it's just a waste of my grader's time to even look at it. Okay, so get it turned in a reasonable amount of time. Then we have homework set number 2, 3, all the way through 7. Okay, so homeworks 2 through 7 are all about op-amp stuff. Homework number 1 is really just, were you paying enough attention in circuits 1 to actually succeed in this class? So it has stuff to do with Thevenin and Norton equivalent circuits, transient analysis of RL and RC circuits, and something else that I don't remember off the top of my head. All right, homework stuff has been, I say explained. Any questions about any of that jazz? Also, I don't know that I specifically mentioned it, but it's probably obvious since every single one of those file descriptions ends in .pdf that I want you to submit it in a PDF format. I will not accept physical homeworks. If you give me something physical, it means it can get lost in the absolute nightmare of a mess that is my office on any given day. If you submit it on Moodle, it exists on Moodle until, as far as I can tell, the end of time, meaning I can't lose it. It is in your best interest to submit things digitally. All right, design projects. So there's going to be some number of design projects. I have 2 currently designed. There should be a 3rd one at the end of the quarter, or towards the end of the quarter on 3-phase power that I have yet to create because I always get busy and forget about it. You will be asked to design some number of things. The first one is going to be on op amps. The second one is going to be on filters. The third one will be on 3-phase something if I get around to it. That will require you to do some amount of circuit simulation using a program called LT Spice. We'll talk about that in a moment. It says a written report, but I don't really mean like some formal report type thing. I just mean some explanation of where the numbers came from. How did you choose these component values? Yada, yada, yada. So support your design with some type of math or intelligent design decision there. You are required, no one gives a crap about my antivirus software. You are required to complete all of the design project assignments. If you do not do so, I will just fail you from the jump. I want to be clear about this. This does not mean you have to get them right. It just means you have to submit something because it's linked to ABET. And so I need to say, students worked on this. Whether you did shittily on it or not is completely inconsequential. It is checking a box. And so this is the ultimate check the damn box. You will fail the class if you don't do them. Okay. Exams. 4 tests in this class. I have broken this course up into 4 effective modules. The first module is on op amps. We are going to get into much more detail than we did in circuits 1. In fact, I would encourage you, if you remember anything from op amps in circuits 1, completely forget it. It's worthless right now. Okay. Our second section of the class is going to be on the transient analysis of second order circuits. So arguably that would be RLC circuits, but it really means any circuit that contains 2 energy storage elements that cannot be combined into a single energy storage element. So we'll have like multiple capacitor systems, multiple inductor systems where they are discrete components. Our third section of the class is steady state sinusoidal analysis. This is exactly what we did in circuits 1 with a few new topics peppered in. For the most part, I review everything that we covered in circuits 1 regarding steady state sinusoidal analysis because a large portion of you guys completely and utterly check out for that section of the class because you've done well-ish on your first 2 exams and stop giving a shit. It's important, so we're going to cover it again. And then our fourth section of the class is on polyphase circuits. Specifically, we're going to focus our attention on 3-phase systems because that is how power is transmitted and distributed effectively in the industrialized world. Things are slowly moving back towards DC distribution systems because of the prevalence of battery energy storage technologies and all that kind of stuff. But we'll talk about that later. Each exam consists of a closed book portion. We'll talk about that in a moment. That makes up roughly 75% of your exam score, and an open book portion to be completed at home. So there's an in-class portion of your test, and there's a take-home portion of the test. The in-class portion of the exam is effectively, think about the level of difficulty of stuff that you did in Circuits 1. That level, if not maybe a little bit easier, if I'm being entirely honest. And about that closed book notes, I usually provide you with an equation sheet. So I would argue that makes it even easier than Circuits 1 because you have an equation sheet made by me. And if we know anything about me, it's that I'm very full of myself and my abilities. The take-home portion of the exam is typically 3-ish problems, each 10 points apiece. I give you, I think, 4 class days or something like that to do it, like not a week or whatever, but you know, something close to a week. Honestly, it should take you no more than 2-ish hours to do all 3 of the problems. I just want to make sure that you guys have enough time to do it with your schedules and all that kind of stuff. The take-home portion of the problems are literally just problems similar to what were on the in-class portion of the exam, except that they require you to use a computer, and I don't want you all to cheat, or at least cheat in front of me. So I allow you to take that part home and work on it over a couple of days. For the in-class portion of the exams, only FE-approved calculators are usable. So the same calculators that we used in Engineering 120 series and Engineering 221 are for use in this case as well. No cell phones, that's a pretty general thing. Grading, the weighting of grades, 20% for homework, 10% for design projects. Again, if you don't do them at all, you just get an F. Exam 1 is worth 20%, exam 2 is worth 20%, exam 3 also 20%, exam 4 also for 20%. And then the little caveat here that you can totally screw up on one exam and it will only count for half, so that if you just have a really bad test day, it's not the end of the world in this class. Let's see, grading scale, standard 10-point scale, syllabus changes. I don't expect there to be any, but if there are, I will change the syllabus and I will let you know what's what. Emergency notification system stuff, COVID-19 policy stuff, counseling services stuff, tentative schedule. No night exams or anything like that in this class. So when we have exams, they're physically here during regular class times and all that kind of jazz. One thing that I want to make you guys aware of for this class date, the end of this month, March 31st, a day I have set aside to just work example problems, I actually won't be here. I will be on a plane to Pennsylvania for a wedding that I'm not particularly thrilled to go to, but whatever, I love my wife, so it is what it is. So what I'm going to do is just probably either pre-record me working some example problems or just upload handwritten solutions of multiple example problems illustrating things. So you guys have a Friday off. We're still having stuff, all that kind of jazz. And then scrolling way down here on the date of exam 3, this is also the date of the senior projects conference, as well as when all of the industrial advisory board meetings for the various programs in the College of Engineering and Science happen. Since I am a program chair and I also teach senior design, I will physically be elsewhere the entirety of that day. So I don't know who is proctoring that test, but it will not be me on that particular exam day, just to give you a heads up. Okay, anybody have any questions regarding the syllabus? All right, so let's circle back around to software things. If I'm on the introduction section, let's see, nope, that's not it. That class meeting number 1, I have already put up 4 links for you all. This one in the top left is where you will download LT Spice 17. If you haven't already done so, I would do it literally right now. And then MathCAD Prime 8.0 is available here. That can wait until later on today. We are going to use LT Spice to do some stuff here in a moment. So I'm going to open my LT Spice up, which means I have to find it on this gobbledygook of a desktop. No. Okay. So I'm going to create a new schematic. And so I'm going to do that by pressing the new schematic button, which is this little bitty button up here in the top left-hand corner. And I'm going to see if I happen to be smart enough to bring my mouse down here, because this will make my life easier. It looks like I did not. All right. I'll have to remember to bring it for next time. So what I'm going to do is I'm just going to put in this particular circuit from our first homework set. Okay. So this is a Thevenin and Norton equivalent circuit problem. No, mine's up in my office. I'll make do with that. It's not going to be that big of a deal. So I'm just going to start at the bottom left-hand corner and start drawing things here. Okay. So I'm going to go into my component list, which is this button here, kind of towards the right-hand side of this bar. It looks like a logic gate for whatever reason. And because I'm going to put in that 30-volt source first, I'm going to type in the word voltage into the search field. And that's going to give me a voltage source. By default, the positive polarity is on top and the negative polarity is on bottom, which perfectly matches what we're trying to put. So I'm going to go ahead and put this in. I'm going to press escape so that I can get wrapped or no longer put other voltage sources in. We'll get back around to that in a moment. Okay. So what I'm about to do, my mouse is over the center. Yes. The word voltage. This thing right here. So with my mouse over this component, I'm going to right click and it brings up this menu that allows me to put in the DC value of the voltage source as well as a series resistance, which means I can treat this as a ideal voltage source or a practical voltage source, depending on if I put any resistance values. I'm not going to put anything into either of these just yet because I want to click on this, advanced tab and show you guys what our true options are here. Okay. So we can also make our voltage source be dependent on time in various ways. Okay. So we can have a pulsed voltage source, which means it's just on for some amount of time and then off for some amount of time. So this is how we could make square waves and things like that with varying duty cycles. We get to define how long it takes for the signal to turn on, how long it takes for it to rise from its initial value to its final value, how long it takes for it to fall from its final value to its initial value, how long it stays on, the period, and the number of cycles. So we can do all sorts of pulse type things there. The next option is for a sinusoidal voltage source, where we get to decide what the DC offset is, the amplitude of the sinusoid, the frequency, the delay time. I don't remember exactly what theta and phi are, but one of them is the phase angle, and then the number of cycles of the sinusoid that we want. We can also do exponential voltage sources. I don't remember what SFM stands for because I've never had to use that. And then this PWL is piecewise linear. So effectively, we can give it different sections of straight lines to construct different voltages as a function of time and add them all together, and it can do that as well. Over on the right-hand side, we could simply put in our DC value for a DC source. Then in this box, if we are doing frequency domain analysis, this is where we put in our AC amplitude and our phase angle. And then this is where we put in parasitic properties if we want to make our model more realistic. For us, most of the time, we're going to be dealing with sinusoids and simple DC values, but for certain projects, it may be useful to use pulse things here, right? So just want to talk about the different options that we have here. I'm going to press cancel and just type in 30 volts right here. I don't need to put a unit on it, by the way. If I type in 30, it understands because it is a voltage source, it will be a 30 volt source. Okay. For resistors, there's a dedicated button for resistors so that you don't have to search for them in the component window. It's the button that looks like the schematic symbol for a resistor. So I'm just going to wire that up here. So this is going to be my one of my 10 ohm resistors. I'm going to press Control R, which is going to allow me to rotate the element. So Control R is for rotating because my next 10 ohm resistor is oriented horizontally. And I'm going to use, that's not what I wanted, my touch screen to make this a little better. And I'm going to wind up deleting that resistor R2 down there that was somewhere dumb in a moment. Just as a heads up, if you want to delete things, simply select the element that you want to delete and then press the delete key. And it'll bring up little scissors, and then you press the scissors on the element to actually delete it. And I don't know why it continues to auto size things, which is annoying me. Let me get this dumb zoom thing out of the way. Now I'm going to include some wires here. So the wire, to put wires, I click this little pencil icon, and then I just play connect the dots, right? So I know that my voltage source is supposed to be connected to that resistor R1 above it. I know that that resistor R1 is supposed to be connected to this resistor R3, like so. And I'm going to go ahead and give myself some space here for where I'm making the next few connections. So that's literally just me running wires. At this point, I'm going to choose my resistor values. So to assign a value to these components, again, I put my mouse over the element and I right click. And I can just put in whatever resistor value I want. Notice also that there is a box for tolerance and a box for power rating, which means if I'm using this to design a system, a real system, I can say, well, I want 100 kilo or 100K resistor, but I know that the ones that I have available have a 1% tolerance, so I can put that in and it will randomly assign a value within a 1% tolerance of that. And I can also specify the power rating, so 1/8 of a watt, 1/4 of a watt, 1/2 watt, 5 watt, whatever, so that I can see if that particular element is absorbing too much power and would cause a failure in my system. So very useful tool. For this class, we're going to be dealing with idealized resistors. So I'm just going to put in the number 10 because I want a 10 ohm resistor and call it a day for both of these. So I've got this thing set up for the interior of my circuit where my 10 amp current source, excuse me, my 5 amp current source and my other 10 ohm resistor is. So I'm going to go ahead and do that. For my current source, I need to go back to that component menu, and I'm going to type in the word current. By default, my current source has a direction down. The current source in our schematic has a direction up. So I'm going to press Control R twice to rotate it in the direction that I want. I'm going to go ahead and right click on this current source, and I'm going to put 5 amps in. Excuse me, I can't read this printout, and press OK here. There are all of the different types of voltage sources that we had. We have the exact same types of current sources. So we can do exponential current sources, sinusoidal current sources, pulse current sources, all that kind of good stuff. Since we simply want a DC current source, I'm just going to leave it for the DC value. I'm going to throw a resistor over here on the right-hand side. This is another 10 ohm resistor. And I'm going to go back and start wiring things again. So I pretty much have the entire left-hand side and the middle portion of the circuit done. So now I'm going to start working on the right-hand side. That is not where I wanted that. So what I'm doing right now is I'm literally just putting the wires in place first, just so that I can show you something for the remainder of the circuit. And now I'm going to throw resistors in. So I'm going to do that 20 ohm resistor kind of in the right middle side here. So if I put a resistor on top of this short circuit, it's going to break the short and place the resistor there. Okay. So that I can kind of map out how things are going to go and then put the resistor in to fix things. Right. I'm going to press Control R and put this resistor on the right hand side. And then I'm going to rotate this guy again and put one up here on the top. These are all of my remaining resistors. So this one up here is a 20. This one here is a 20. This one here is a 10. And then I have that voltage source. It's the only thing left. Much like with the resistors, it broke the short for me and placed the voltage source there. This is a 20 volt source. And now what I'm going to do, and this isn't entirely required, but just to make it look much more similar to what we have on the page, I'm going to give myself a little stub of wire right here for terminal B. I'm going to give myself, that's not what I wanted to do yet, a little stub of wire over here for terminal A. So this is a DC circuit. There are only DC sources in it. So if I go up here to where it says simulate, and I edit my simulation command, I have multiple different types of simulations that I can run. Okay. Transient analysis simply means exactly what we did back in circuits 1. It's just telling us how our circuit is behaving as a function of time. Since this is a DC circuit, that's more information than we would actually need. Okay. Then we have AC analysis. So this is what is commonly called frequency domain analysis, where we're looking at the amplitude and the phase of our signals. This is what we are going to look at when we're dealing with filters and things like that. We have DC sweep. So that effectively means we can just change some parameter and then run the simulation over and over and over again to see what the effects of that changing parameter are. Then we have a noise analysis, DC transfer function, and then over here on the right-hand side, which is what we're about to do, DC space OP space PNT, DC operating point. So what is the DC operating point of this circuit? It is going to calculate every voltage at all of our different nodes, the current flowing through every element, and then multiply those two numbers together to give us the power that is dissipated, absorbed, or supplied by our elements. So I'm going to come over here to DC operating point. It's going to give me this little bit of code, just .op tells it to run a DC operating point command. And then I'm just going to put this somewhere on my figure that's out of the way. So this is the SPICE code that's telling our simulation tool what to do. And then I'm going to press this little running man icon, which is to run the simulation, and it's going to give me an error. The error says this circuit does not have a conduction path to ground. Please flag a node as ground. So LT SPICE effectively works by doing nodal analysis on any and everything that you throw at it. You must specify a ground in order for this to work. So as we should all know by this point, we can choose whatever the hell we want to be our ground, okay? For this homework problem, at least in part A, we are trying to determine what the Thevenin voltage is seen between our terminals A and B, where A is on the left-hand side over here, and B is on the right-hand side over here, with the positive polarity voltage reference on the left. So I would argue, just purely from doing a simulation, we should choose B as our ground. That way, whatever voltage we see here at this node is our Thevenin voltage. Okay. So I'm going to choose ground from the little option up here. There's a designated thing. I've assigned ground to that node. I'm going to hit that Running Man icon again. And now it gives me effectively a list of things. So it tells me that the voltage at node 4 is 17.5 volts. The voltage at node 5 is negative 12.5 volts. The voltage at node 3 is 20. The voltage at node 1 is 22.5. The voltage at node 2 is 20. The current through current source I1 is 5. The current through whatever resistor R6 is 1/8 of an amp, et cetera, et cetera, et cetera. So it gives me a bunch of information, but I would argue that that information isn't super helpful right now because we don't really know how to interpret things. So I'm going to close this window out. Okay. So we can do two things here. Okay. If I mouse over any node point, and this is hard to see, let me move this thing out of the way, right? So if I put my mouse cursor over any section of wire, way down here in the bottom left-hand corner, it tells me this is node N002. So this is where node 2 is. Its DC operating point is 20 volts with respect to ground. Okay. If I move my mouse cursor over an actual circuit element, it tells me that the current flowing through this circuit element is 125 milliamps, and that is dissipating 2.5 watts of power. So effectively, all of the information from that big table is stored in the schematic itself. So that if we mouse over any node, so any wires, we can figure out what the voltage is. And if we mouse over any element, we figure out what the current and the power is. Okay. So for instance, the current flowing through this resistance R4 is negative 9/8 of an amp, and it is dissipating 22.3125 watts. So dissipation positive here means absorbed power. That's fairly obvious because resistors can only absorb power. If we were to mouse over here for something that we're actually interested in, we can see that the DC operating point of node 3, which is the terminal A that we were looking for as our positive polarity reference, is 20 volts with respect to ground. So that's our Thevenin voltage. Let's make things slightly easier to figure out what the hell's going on now. Okay. So what I'm going to do here is I am going to go to this symbol right here, which looks like a little signpost with the letter A on it. What this lets me do is label a node with some particular text, right? So I can call it ground, I can call it common, or I can call it something else. I'm going to opt for something else, and I'm going to be real lazy. I'm going to call it VTH. And I'm going to drop that label right there on that node. If I run that simulation command again, now it tells me the voltage at node VTH is 20 volts. So I can see right from the jump what the hell my Thevenin voltage is. Okay. So LT Spice is as smart as you tell it to be. And it starts off by being real dumb, okay? So this simulation told us what our Thevenin equivalent voltage for this circuit is. We didn't do any math whatsoever, which this hopefully makes it very obvious why I didn't mention this once in circuits 1, because with web work problems, you could effectively do everything without ever doing any math whatsoever, and you'd have 100 on your homeworks and zeros on your exams because you wouldn't know what the hell you were doing. Okay. So let's look at part B of this problem, right? So part B of this problem is finding the Norton current. So what do we need for Norton current? How do I find the Norton current? You guys have all had a class on this. So I need to short out my terminals A and B. Okay, so I'm going to do that with a wire. Does it remotely matter that ground is there at that node? Not at all. Okay. So I'm going to run the simulation. So now I'm simulating the circuit under a Norton equivalent circuit condition because I've shorted out my terminals A and B. I have all of this information. Again, doesn't really tell me anything other than now my Thevenin voltage is also ground, so it's not even showing it up because I've shorted it to ground. So it's just useless information. If I mouse over this wire, it just tells me this is ground or the voltage is 0. It doesn't give me the current at all, right? Because it only gives me the current through elements, and it only tells me voltages when I'm at wires or nodes. So how can I trick this thing into giving me what I want? So I can put in a very, very small resistor. If I put in a 0 ohm resistor, I think it'll behave dumbly. I'm not 100%, but I think it will behave dumbly. So instead, what I'm going to do is I'm going to put in a 0 volt voltage source, which I know has exactly no voltage drop over it. So it is a short circuit so that I'm not getting something close to the answer. I'm getting the right answer, and it will have an element for me to measure the current through it. That's the wrong thing. That is also the wrong thing, sorry. Nope, I wanted a voltage source to measure current. Sorry, space trucking here. I'm putting it such that the positive polarity is on the left. We'll talk about that in a moment. And I'm going to give it a DC value of 0. And I'm going to press the run button. So now, if I look down here, I of V3. So this is the current flowing through the voltage source identified on our schematic as V3 is 2 amps. And obviously, if I mouse over it, way down here at the bottom, it also tells me that the current is 2 amps. Great. What direction is the current flowing in? Beats the hell out of me. So I believe it's flowing to the right. I don't know for sure, okay? And there's nothing on this figure to explicitly indicate that. So I'm going to change my simulation very slightly here. It's going to give me the same information, but I'm going to change my simulation. So I'm going to edit my simulation command. I'm going to do a transient analysis. And I'm just going to tell it to stop running after 1 second. It's a DC circuit, so it really doesn't matter what value I use here. And it put that semicolon in front of the OP to effectively comment it out, saying, don't do a DC operating point, do the transient analysis. So if I run this simulation, I get a big empty box. Because again, LT Spice is as dumb as it can be until we tell it what to do. Okay. I'm going to right click down here simply to make this schematic fit better. So zoom to fit. And when I mouse over this thing, hopefully you guys can see it. What this symbol is a current probe. and the arrow tells me the direction that the current is flowing, right? So if the arrow were pointed to the left, I would be getting the current in the wrong direction, okay? Now I can make this current show up on my graph. If I simply left click here, it shows me exactly 2 amps with this particular direction. If I happen to have it set up and it gave me the wrong direction, if I right click here, I can add traces and I can tell it what to do. So I could say, actually, I want negative the current flowing through that voltage source V3 based on the direction that was indicated in the problem statement or something like that. So I can just type negative and then click this. And now it gives me the current in the opposite direction. I can add currents together. I can add all kinds of weird things together. And we're going to do this. We're going to use LT Spice later on when we're looking at transient analysis problems where we are simply going to simulate our circuit. And then we are going to type in a mathematical expression and compare the two things. And if they perfectly match, then obviously we did it right because our analytical solution matched the simulation. If we made an error, it's not going to tell us where our error is, but we're going to see very obviously that there is an error because our work doesn't match the simulation. So what I expect you guys to use LT Spice for in this class is a method by which to check your work, because there's nothing that we are going to do in this class that you can't simulate and see whether or not you did it right. Okay? It does involve you knowing how to use LT Spice in order to see whether or not you did things right, but there's nothing in this class that we're not going to be able to simulate. Okay. All right. So let me kill this and let's do exactly what I just mentioned. Okay. So let's say that I have the following circuit. This is going to be a really simple transient analysis problem. Okay. Let me draw something here. Where did my picture go? There we go. So this is going to be an absolutely trivial transient analysis problem, okay? So let's say that we have an 8-volt source, a 10-ohm resistor, I need to throw a switch in here somewhere. This is the circuit that I'm analyzing, and I want to know whether or not I'm calculating the voltage across my capacitor correctly, right? Very, very straightforward. What would we do to analyze this problem? What did we learn to do in circuits 1? Some of you guys had it last quarter. Come on. I gave you a pretty straightforward step-by-step process. Analyze the circuit at t is equal to 0, minus, analyze it at t is equal to 0 plus, analyze it at t is equal to infinity, calculate the time constant, throw the results of those 4 steps into the generic equation, and we are done, right? So analyzing this at t is equal to 0 minus, at t is equal to 0 minus, we're at DC steady state, so my capacitor looks like a what? An open circuit, okay? My switch is open at t is equal to 0 minus as well. So I would argue this is what my circuit looks like at T is equal to 0 minus. So what's my capacitor voltage? 0. It's not connected to the voltage source, so why would it charge? Over here, let's talk about T is equal to 0 plus. I'm not even going to draw the damn circuit. Why do I need? Why do I not need to draw the circuit? Exactly right, because the capacitor voltage does not change between 0 plus and 0 minus. So if it was 0 volts, it must continue being 0 volts. Absolutely right. At T is equal to infinity, I'm at DC steady state, but now my switch is closed. So I have my 8-volt source, my 10 ohm resistor, my 5 ohm resistor. My capacitor looks like an open circuit. So what's VC at infinity going to be here? Voltage drop across the 5 ohm resistor, absolutely right, which is going to be, I think it's going to be 1/3 of 8, because I know how to use voltage division. I thought you guys did too. Do I need to recover that? I mean, again, I feel it's not my intention. Well, it's not my intention to sound like a smug asshole either. But if you have questions, by all means, ask them, okay? So I see an 8-volt source in series with a 10 ohm resistor in series with a 5 ohm resistor, which to me looks like the perfect place to apply voltage division here, right? So using voltage division, I have my known voltage, 8 volts, multiplied by the resistor over which I'm trying to find the voltage drop, which is the 5 ohm resistor, divided by the sum of all of those resistors in series, which in this case is literally just 10 in series with 5. So 5 over 15 is the same as 1/3. So to me, this looks like 8/3 of a volt. Now I need to calculate my time constant. All right. So because this is an RC circuit, what do I need? R and C, exactly right. What's the equivalent capacitance of this circuit? There's only a 1 millifarad capacitor in it, so I would argue that it's 1 millifarads. Okay. So CEQ is 1 millifarad. Okay. I think we can all agree on that without a whole lot of calculation. To determine our equivalent resistance, what do we need to do? We need to look in through where the capacitor was connected at a dead network, because we're finding the Thevenin equivalent resistance from the perspective of the capacitor. So my voltage source is off because I need a dead network. Here's my 10 ohm resistor. Here's my 5 ohm resistor. These open circuit terminals are where my capacitor was. And this is my equivalent resistance during the transient condition, which means my switch is closed, right? So what do I see? 5 in parallel with 10, which looks like 50 over 15 or 3 1/3. All right. From here, my voltage drop across my capacitor is, let's see, 0 volts for T less than 0 minus. And there's going to be 0 volts minus 8/3 of a volt, e to the minus T over, well, I didn't calculate tau here, so let's do it. Tau is REQ times CEQ. So that's 1 millifarad times 3.333 ohms, which is going to be 0.00333 seconds. Doing this in my calculator so I can easily do the reciprocal. So 1/300 seconds. So tau to the -1 is 300 per second. So I'm just going to call this e to the negative 300t plus 8/3 of a volt for t greater than or equal to 0 plus. Anything wild or groundbreaking here? This was supposed to be covered in circuits. All right, so we have an analytical solution. So let's simulate this circuit and see if our analytical solution matches the simulation. We're going to be doing this extensively in this class. Might as well get started on it today. Reconnecting the keyboard will make my life easier. Coming over to LT Spice, having a new schematic. So we're going to simulate this thing for t greater than 0 plus. Okay. We could simulate it for t is equal to 0 minus or less than 0 minus simply by drawing our circuit with an open circuit and then doing a DC operating point simulation. Well, we're going to say that we got all that part of it right because it was pretty obvious the answer was 0, right? So I have a voltage source. It's 8 volts. I have a resistor that goes there, a resistor that goes there, a capacitor that'll go over here, and now I'm just going to wire stuff up. You do not have to do this by any stretch of the imagination. Let me put in these values before I forget about it. 10, 5, 1 milli. Just to be clear here, M is for millifarad. Capital M is not for mega. Capital M is also milli because LT Spice is done. Okay. If you want mega anything, you type in MEG. Just to be clear, not going to be an issue for us for quite some time, but it is going to be an issue. So I just wanted to be very, very clear about that. So circling back around to things, whenever I'm trying to do a transient analysis to determine the voltage drop across my capacitor, I typically choose my ground to be the negative polarity terminal of the capacitor, which in this case is going to be this bottom node. This is something that isn't necessarily required, but I have had it give me errors before, literally years ago, so chances are it has been updated to fix this. But I don't put my ground directly on this node. I give myself a little stub of wire and then connect my ground to that stub of wire, just because a couple of times LT Spice pissed me off. All right. And now, just for the sake of argument, so that it's really obvious as to what we are actually finding, I'm going to label that node VCs that I know what to look for my capacitor. Okay. So we're doing a transient analysis here with an energy storage element. So we're going to have to do one other thing here because we need to incorporate how the system was working at t is equal to 0 minus. And we do that by writing a spice command to set the initial condition on the system. So if we come over here to this little thing that says .op, I feel like the zoom thing is in the way of telling us what the menu is actually giving us. It's just not showing up for whatever reason. This is where we enter in spice commands or spice text, right? So this is just going to open up a window. Because I only have one energy storage element, I'm just going to write one line of code. You need to pay attention here because the syntax is incredibly important. I'm being facetious. I mean, it is important, but this isn't mind-blowing amounts of code or anything. Dot IC, because it's an initial condition. Now I'm going to say the voltage, so that's V, at, so I'm opening up my parentheses, VC, which is the node that I've labeled so that I tell it exactly what it is that I'm looking for, or tell it exactly what it is that it's doing, close parentheses, is equal to 0. Because the initial condition on the capacitor voltage was 0 volts, right? That's all the code, yes. Not to my knowledge. I don't think it matters at all. I just happen to write everything in capitals. Yes. I don't think definitely needs to be a space between the IC and this V, but all the other spaces I also don't think matters. And I'm just going to drop this down here somewhere out of the way. And I'm going to tell it to run a transient condition here, or excuse me, a transient analysis. I need to tell it how long. So I know that my time constant was 1/300th of a second. And I know that it takes me roughly 5 time constants for this signal to completely change. So let's make it a little bit longer than that. Let's make it, let's see. So 3/300ths would be the same as 1 millisecond. So let's do 3 milliseconds. All right, I'm going to run my command. And I had a leftover graph from something else. So I'm just going to move this down and make this larger. So I'm interested in the voltage. So I'm just going to put this voltage probe at the node that I'm looking for and left click. And this is what I get. And that definitely does not look to be enough time. So I must have done the mental math in my head incorrectly. Yeah, 3 milliseconds isn't even one time constant. So let's multiply this by 10. So let's do 30 milliseconds. I'm going to go back and edit this simulation command and make it 30 milliseconds instead. Rerun things. And now we can see, if this dumb thing isn't in the way, that it actually settles to some value. I'm going to change the color of this from green just so that it's a little easier for you guys to see. So I believe I can just right click there and tell the color to be blue. And now you guys can see it a little bit better. All right, so this is what the simulation tells us is going on. It starts at 0 and it ends up somewhere close to 2.7. I'd be willing to bet it's 2.66666 repeating, or 8/3. But let's see what happens. I'm going to right click this and I'm going to add a trace. And instead of adding any of the stored data, I'm going to write a mathematical expression. Okay. So this should be negative 8/3. So that's 2.667 volts. That'll be good enough for me. Times the exponential of negative 300 times time plus 2.667. Right, so negative 8/3 times e to the negative 300t plus 8/3, which is exactly what we analytically got a moment ago. Press OK. I'm going to change this to red so that, again, we can see it a little bit better. So how do we interpret this? The red curve has completely overlapped the blue curve, right? The red curve is what our analytical solution was. Since it's completely overlapping the simulation, it means it matches the results of the simulation. So we must have done the problem correctly. Now, there are instances where we have done things correctly and it won't completely look right. And so I want to talk about that very briefly on how to check things. Okay. Notice that there is an axis on the left-hand side of the screen and there is an axis on the right-hand side of the screen. If these axes aren't the same, that's a problem. That's a very common mistake that I see students make, right? So we can see that this one starts from 2.7 and goes down to 0. This one also starts from 2.7 and goes down to 0. Since the axes are the exact same scale on both sides and the curves overlap each other, we did things right. But if, just for the sake of argument and to screw with you guys, I change this to top value of 5 in 500 milliwhatever increments, they don't look like they overlap anymore because the scales are different, right? So if you don't verify that the scale on the left-hand side and the scale on the right-hand side are the same thing, you're not comparing apples to apples. Okay, so that's just something that you need to look out for. There are a couple of other nuances that we're going to have to deal with. For instance, LT Spice does everything in degrees, not radians. And so we usually express angular frequencies in radians per second, which means we're going to have to add a conversion factor of 180 over pi. LT Spice also does everything with a sine function as its reference. And we have all gotten into the practice of doing everything with a cosine function as a reference. So we're going to have to remember to subtract 90 degrees and all that kind of stuff. But we'll get to that later. All right, so I have ranted for a solid hour and 11 minutes and completely forgotten to take roll. So let me do that real quick and then we'll be out of here for today.